To everyone on so far, thanks for joining. Most of you know me. I'm Aaron Burney. I'm the Education Program Manager for IPC's Education Foundation. We have a follow-up to our webinar from last week. I will reintroduce Chris Jennings. If you met him last week, fantastic. If you have not, welcome. Chris Jennings is the Manager of Global Training for Altium and an Altium Designer, and has been a user for 15 years. He has a BS in Electrical Engineering from WPI and is a CID+. His extensive career includes the following design types: digital controllers, low power battery operated RF and high current, as well as the design of both full and semi-custom ASICs.
ASICs, yep.
ASICs, very good. He was the system architect for the first robotics competition in 2009, control system, and invented an indoor GPS system for robot competitions. Chris coached the high school first robotics competition team, 1519 Mechanical Mayhem, for 14 years. So that's a brief bio of Chris Jennings, who's going to lead our webinar today. And if you'd like to say anything else, go ahead. But for now, I'll turn it over to Chris. Just a reminder to everybody, you are welcome to drop questions in the chat or in the Q&A section. Chris will be presenting most of the time, so I'll do my best to facilitate and ask questions. I probably won't jump in and interrupt him, but you never know. If there's a compelling question, I may.
Yep, no worries.
Okay.
Thank you, Aaron. Yeah, I've had a few decades of experience in the electronics industry. One of the things that it was interesting to me about this particular topic, schematic capture and schematic design, is there are things I wished I'd learned when I was in college that they didn't teach, that you only learn over time. So that's partly what I'm going to try to give today, the benefit of some of the College of Hard Knocks, as it were. So let's just jump right into it. Share my screen. So again, this is Introduction to Schematic Design. Okay, here's our agenda. Again, 6 basic topics or areas. Really, number 3 and number 4 are a continuation. It's just, I just try to keep it small and bite-sized on each of the slides when we hit them. But in brief, you know, you need a specification. You can't hit a target if you haven't defined what it is you're aiming for. With design complexity, you have options for organizing your schematics. So the difficulty you have is, how do you clearly communicate the design intent? And that can be done in a number of ways, and we'll talk about some of that. What is a great schematic? What do they look like? What are the attributes? There are very minimalist schematics. I've seen some really bad ones as well, and we will try to at least give you the hints as to what constitutes a good and maybe even a great schematic. And then there's ways to add value to the schematic, and by value, there is both intrinsic value for test, for example, and there's also value for the layout effort. For many of you who are in college, you're going to probably be both the designer and the layout engineer, but typically in the industry, those are 2 separate groups of people. And there's a huge gap in communication and understanding between the designers and the board layout people. And so there's ways to add value to the schematics that provide guidance for the layout team. And we'll talk about that. One of the dirty little secrets is parts choice. It's more important than you know. Can't tell you how many times I've released a design, got the prototypes back, everything was fine, and we start to go into production, and the purchasing says we can't find these parts, and there's no equivalent. So you end up having to take a hit shipping schedule-wise. You have to redesign the board and potentially redesign all of the logic around it. So parts choice are really critical, and nobody really talks about how important that is. And then the last part is checking your design. Typically in school, you're checking your design personally. You don't have a team that you're working with. As soon as you get out of school, your employer is going to want to have your schematics verified and possibly even the PCB verified before you go into production, because you're talking about a lot of money. And the design checks are really useful and can be very helpful. So I would encourage you to not skip those, obviously. So jumping into it, what am I designing? Starting with a specification, all too often when you start a design, you can lose your objective along the way because in many cases, there may not be a very clear specification. I've learned early on to ask questions, to kind of talk through some of what the real requirements are and what the unwritten requirements or expectations. And just between us, sales will always oversell and hope that you can over-deliver. So it's critical to have clear specifications so that you can say, I delivered and I delivered more, or I delivered as much as you were expecting. Again, without a specification to refer to and to be your guide or guardrail, you run the risk of not actually creating what's necessary. For me, I like to look at the big picture. And by that, I mean, I start at the top level and work my way down. I've done both singular board level design as well as system level design. And now, so even if I'm doing a singular board design, I want to understand how it fits relative to the rest of the system. That gives you the opportunities to do a better job, to integrate more completely or more fully. And it allows you to have better functionality. It also makes potential integration and testing much simpler. So it's very important that you can start with the big picture so you understand where you fit in, even if you're only working on a very single board. One of the things that you'll learn, again, is never reinvent the wheel. Never reinvent the wheel. If you have a power supply design that's worked for you multiple times, go ahead and use that in your next design. It's lower risk. It's faster because you don't have to redesign it. You don't have to relook it up. Obviously, you want to make sure you can still get the parts. But having experience with a design and with the components of a design can be a significant advantage. Again, you want to ensure that you have success with your design, and not having experience in every aspect of it is greater risk. Significant risk, maybe, maybe not, but I typically reuse power supplies. I've reused some RF chain logic on numerous occasions for different customers. It really does help. So again, use what you already have if you've used it in the past. Altium has a concept called design reuse. And so we typically allow you to take an existing schematic. In this case, I'll show you an example of the power supply that I used. That power supply schematic was used for multiple opportunities for a couple of different jobs along the way. The advantage, again, I knew it worked. I knew the parts were available. And I'd already done a layout a couple times with it, so it was a lot faster to get the layout finished because I had some template and guides for that layout. Again, it's critical. So when you want to clearly communicate your design intent, you want to utilize the schematic structure to aid in the circuit understanding. And let's jump into Altium Designer to kind of talk about that. Here is my beloved WC topping, and if you were here on my last call last week, you know that stands for whipped cream topping. So named because it sits on top of a Raspberry Pi single board computer. That's a little tongue-in-cheek for all of the Essentials class students that we've taught for the past 5 years, actually, for Altium. Most of the time, we don't even tell them what WC topping stands for. Some of them figure it out along the way, and I give them a little bonus candy bar at the end of the class when I used to teach, just if they figured it out. But if they've spent any real amount of time with me, then they know that I like, you know, to do a little tongue-in-cheek, little play on words. And so usually 2 or 3 out of the 10 would get it, sometimes more, sometimes less. But this particular design has been used extensively, as I said last time, for all of our essentials classes. It has most of the elements. And let's jump to the power supply. This is a power supply that I've used, designed for, like I said, almost 6 years now. Some of it's been updated over time, newer components, but basically the same configuration, the same operation. And as you can see, there's a lot of information on this particular schematic. And this can help aid your understanding for what you are trying to do, even if it's not you. I mean, typically, again, when you're in school, you're wearing all the hats. You're doing the design, you're probably doing the layout, and you're doing the testing and debugging. But in the industry, you will be doing some of those functions, not all of them. And anything you can do to make it easier for others to understand your design will make that design more valuable and more readily accessible. And that's somewhat critical. But this particular design has a few blocks. It has a processor interface block, digital I/O block, CAN interface, a relay I/O block in this power supply schematic. So the logical block structure of this is pretty straightforward. This is 5 pages. It's a flat design, and a flat design is sufficient for this level of complexity. If you start talking about a full-up microprocessor or something a lot more complicated, for example, this is the spirit level design, and this is done in a hierarchical fashion. Again, once you start going up in complexity, or you can't fit all of the design conveniently onto a couple of pages, and they're not logically associated with each other, it's best to have a block level approach, higher level. That allows for certain things like, and let's zoom in, you can see the connections between, this is a LCD switch, and this is the main controller here. You can see that there's a LCD bus, for example, here. You can see a test. You can see the switch settings as a bus coming in. It makes it a lot clearer exactly what is going on in this particular design. These are obviously headers that provide some user I/O functionality. So this is a little bit easier to understand because it's at an abstract level. You know, here's the FPGA, which is just sort of ugly in terms of how it's laid out. A lot of times you'll get FPGA circuit symbols that don't look like this big blob. This is probably the limit of what you'd want to have as a singular entity. Usually you do a multi-part. And by multi-part, that would be something like you would have, you know, all of these IOs as a block in a single entity. And that makes a big difference because now you can place those where you need in the schematic, and it's not necessarily all in a single page. So this is kind of isolated, and it makes it difficult for you to understand necessarily where all these things go. Again, you have to go back up to the top level, right? And the top level makes it clearer. So hierarchy when you need it, flat if you don't need it. Don't make things more complex than you don't have to. You don't need to add layers just because you can, I guess, is one of the things. Let's see. So again, you want to make sure that you have your schematic structured so that it's easy to understand the flow. Let's see, looking at the project, yeah, we talked about the project overall. We talked about hierarchical. Okay, just making sure we got all the stuff based. Again, use flat or hierarchical design based on the complexity. Don't make it more complex than it has to. But a lot of times having hierarchy, even in some of the simpler designs, can demonstrate more cleanly data flow, for example. That's important to understand. Let's see. So creating great schematics. There's basic elements that you need, and let's go back to Altium. At a minimum, we'll go to the digital I/O. At a minimum, you need the components and their wires to interconnect them. Now this, and I'm going to zoom in here a little bit. Move this over here. Actually, we'll just zoom in on this one section here. Now, there's a ton of information here, but you don't need all of this information at a minimum basic level. And by that, I mean, let's see, drawing objects text. I'm using the properties panel here so I can select certain things and leave everything else. So let's just select this and hit delete. This is really the minimum that you need. Your components and the wires, that's all you really need. Is that useful? Well, it'll work. But if somebody walks up to this and starts to look at this and they're going, what's connected to what? And I don't quite understand. There's a lot less information here than there is if I just hit Control Z and leave it back. So clearly, with a label like digital IO expansion SPI to 16 IOs, it's kind of clear what this block of logic does. You don't have to know what an MCP 23S17T does, because that simple label makes it clean and easy to understand. You have labels on all of your nets. This is a particularly important label here, reset. One of the questions that should come up, and it better come up basically, in a design review is how do you start the machine up? What's the reset process? Well, here, this is a resistor and a capacitor. So when the power comes up initially, U11 is in reset mode. And that's a very constant, easy thing. It's very easy to see. It's easy to understand what's going on. And here's all your IOs. And again, this allows someone who doesn't know your design to look at this and fairly quickly grasp what's going on in this particular page. And likewise here, this is a series of through-hole connectors that plug into an external module. It's an MPU 9250. It has a gyro and it has accelerometers on it. It's for basically navigation for robot. That's what it was used for here. We didn't use the mag because the mag gets the magnetic sensor gets thrown off. Magnetic compass gets thrown off by all the DC currents running around. But the accelerator and gyro worked pretty well, and it was used for guidance. So here you can see what's connected to what, so there's no confusion. Here's the part that you are using and have designed to. And one of the critical things when we talk about adding value, not just a good or a great schematic, but adding value, is this little bit right here where you say, this is an I2C bus and here's the I2C address. That way, 3 weeks from now, you get the board back, you plug the module in, you're trying to program the processor to talk to this. It's like, oh, let me look up what that address is. Having the address physically in the schematic is such a stupid, easy help that you'd be crazy not to do it. So these are the kind of things that add value, make it easy and transparent downstream, and make it somewhat obvious. Even if you haven't used this design and are not familiar with the design, you can look at this and your programming staff could look at this and say, oh, that's how I get access to the MPU. So this just saves time in the long run. And that's one of those things that I think is very critical, that having understood, because I've been there. You walk into a lab and you're going, okay, what's the address for this again? Well, if you have the schematics, you can just look. It's simple. You can also do things like attach, for example, this particular header, not that I've done it, but you could actually attach a data sheet for that MPU part. So there's ways of doing that. So that's another way of adding more value to your schematics by adding all of these helps that, again, 3 weeks from now, you may not remember what that, I mean, I don't even remember what the IC address is now, and I was just looking at it, but 3 weeks from now, you definitely won't know what it is. So again, saves you time, saves you aggravation, saves you mistake and frustrations. Again, simple things like net labels, very critical, especially something important like reset. I could also see things like buses. That's a very useful thing to have. It just makes it neater. It makes it cleaner. And when you have buses at a higher level, what you end up having is a much cleaner view of how data flows around, how your address flows, and all of your control signals. Again, communicating design intent is critical. But so basically, you need the components and the wires. But you can add so much more. It is just so much better if you have the rest. Again, we talked about adding nets. We talked about net labels, I should say. We talked about additional things that can help. For example, the notes. Those are what I would call design intent aids. The other thing that's obvious that I didn't point out is this graphic here. It doesn't take any time to do, but now it makes it very clear that this logic block right here is for my digital I/O. And it makes it easier. Again, this is a pretty straightforward, simple example. But if you have a large sheet that you've put a bunch of blocks of logic on, this makes it really nice and really understandable, not just for you, but and for others looking at the schematic. But later on, if you had handed this off to a layout guy, he could look at this and select all of these components basically, and then be able to place them as a group within the PCB. And that would be, actually, that was something we can do. And we'll turn everything off and say, I just want components, and then select all of these guys. So that should select all the components. I am hoping. Got to open up the PCB. We may have to reselect them because the PCB board was not open up. Isn't that beautiful? 3D. I love that. We'll go back to 2D. So let's go back and select these components. And now you see all the components that were in that block. You could actually move all those components as a block because they've been selected from the schematics. So again, the simple fact that you have this graphic that delineates this block of logic makes it easier for your layout engineer downstream to have that logic together. Now, obviously, all the interconnects will drive it together, but this makes it a lot faster. So that's how you add additional value downstream. Aaron, if you see questions pop up, please let me know because I can't see any of the questions, just so you know.
No problem. Nothing direct for you yet, but
Okay.
I will keep monitoring.
Making sure.
Yep, feel free to ask anybody.
Yep. So, design intent. Again, so the intent of your design is not always obvious to anybody except you. And the other thing I will say to that is even sometimes to you 2 months later, what you were trying to do may not be clear. So put notes, put hints, put things like, we'll go back here to the power supply. This note right here. Note, use 114555 P2 staple to fasten the Anderson connectors. All of these are Anderson connectors. They're typically used for robotics applications. They're robust, they're keyed, so you don't accidentally miswire things and misconnect things up. But in order to securely attach them to the PC board, you don't want to forget you want to use a staple to hold them down on the board. So when you're plugging in and out, you don't rip them off the board. So these are the kind of helps that you might forget between sending the board out to get fabbed and now it's assembled and now you want to start testing it in the lab, but all of a sudden you realize that your power connections are damaged or getting ripped off. Well, that's because you forgot to put the staple. So again, these sort of notes can save you grief downstream. So how else can we continue to add value? Again, notes like the I2C bus address is critical. The other thing that is very useful is PCB layout aids, like we talked about, the graphics, but also net class definitions. And what is a net class definition? Funny you should ask. This is a parameter that gets attached to a net in Altium. I'm sure there are equivalents for other tools. I can only really speak to Altium. A net class provides a way of identifying nets. In particular, it's used for the PCB layout. If I call this as a net, this is now a net class, and it is it's called power nets. That's the name of this net class. So the 12-volt net, power net, is part of a net class called power. Likewise, the 5-volt net is also part of that same net class. And you can now write rules in the PCB and address the net class and say specifically, I want, let's see, rules, drag these guys over here, electrical and routing width. So here's, quite coincidentally, not, a net class-based rule. So this rule basically says those nets that you've attached that net class directive to can have a preferred width, or should have a preferred width, of 30 mils and can be as much as 100 mils. Whereas the standard default rule is 10, 15, and 20 for the widths. So this is a way to let the PCB layout engineer know that these particular nets need to be treated specially. There's also a schematic width constraint here. The net class is for the CAN bus. The CAN bus requires very specific widths for impedance matching. That rule is done here, again, based on having the CAN bus directive here and here on the two CAN bus connections. So again, you can now provide with these type of net classes a number of things. You can provide a way to create a rule, and specifically, and more to the point here, let me open this properties panel up a little bit more because this is critical. You'll notice I don't just have a net class named CAN. I have width and clearance constraint rules built into the schematic. And in Altium, the schematics rule everything. Everything should be driven from the schematic into the PCB, not the other way around. Funny but sad story, I actually had a customer place components on his PCB without a schematic, place components, and then run traces to them and hard define each of those nets so they all matched up and there wasn't shorts. And they went through all this process, and then they wanted to generate schematics from that. And I had to tell them the sad news that that's not how it works. Everything should start from the schematic. And needless to say, he was a little upset and had to do everything all over again because nothing matched anything anywhere. So don't make that mistake. Obviously, start with the schematics, drive everything into the PCB. And in this case, you can not only create net class for writing rules, but you can also add the rules here. Now, in this particular case, this is, you know, a useful case for the CAN bus because you need particular connections. But some of our customers that I've physically been on site at have very high voltage nets, like solar panel, power supplies, rectifier, inverter type schematics. They very, very clearly need to label all the high voltage lines or all the high current lines so that they can point that out to the layout engineers. I think it was roughly 20 designers to a layout engineer at that particular customer. So obviously the layout engineer doesn't know all of the ins and outs of each of the designs, but when they get something like this, where they actually have a rule that says, hey, this is called a high power class, and they put rules in there like clearance constraints. You need to have 400 mils of clearance or whatever the number was. Some of these boards, by the way, which I was shocked at, I'd never seen a board this large, were 3 foot by 4 foot. Was the PC boards they were doing at this particular place. They had their own special fab house that did this. I'm like, you guys are nuts. But it's because of all the constraints that they had to have. It's because high voltage, you know, 100, 200 amps, I mean, they had multi-layer boards of 4 ounces, I think. I mean, it was just insane. It was a very, very specific niche market in terms of what they were creating, but they used that extensively in their schematics. So there was no question in the layout engineer's mind what was going on, where the critical points were, and how to avoid potential failures in the field. Because if you don't have enough clearance, the board will fail. It'll arc over, and that's a very unhappy circumstance. If you've ever experienced board arc, it can be very exciting, I guess, is one way to describe it. But again, this is the sort of thing that, do you absolutely need it for your schematic? No, not at all. However, it is really helpful. And here's the other hint, aid. This block over here is all at 3.3 volts. This block here is in the 5 volt range. There is a conversion, and I needed to ensure that it was very clear what was 3 volts or 3.3 volts and what was 5. There's a couple places in this particular design where I was crossing back and forth. In one case, I had to use a translator chip because I was going from, I think, 3 to 12 volts. But again, this makes it very clear so that you don't accidentally, while you're wiring something up, put something that's a 3 volt level in a 5 volt or vice versa. You don't want to get into trouble. Again, this keeps you from getting into trouble, and also, again, makes it clear what's going on.
Chris, is it common to change voltages?
Yes. Yes. Quite often, and I'll show some of my age. When I was first doing design, everything was 5 volts for logic. Everything was 5 volts. There was also Echo, which was another ugly animal, and nobody liked Echo because it was a real pain. But the general logic that was used was a 5 volt level. And as speeds increased, and as we started putting more and more onto the die so that the chips got more and more complex, the biggest problem that ICs have was getting enough power into the chip and getting it distributed across the chip. And the second level problem, but as significant, was getting the heat out of the chip. And the basic physics say that if you lower the voltage, you can save significantly on the power. Your power budget is much lower when you have lower voltage. So there's a couple of things you can't change. You can't change basically the capacitance that you're driving, because that's based on the geometry in the chip. But the more the more you lower the voltage, the lower power you have, and that makes it easier because it's less heat. But that was driving the IC industry, and the IC industry therefore drove the design industry. So we went from everybody did 5 to some people did 3.3, and then pretty much everybody wanted 3.3, and now there's 2.5 and 1.8 core voltages, and even lower in some cases, 1.3 I think I've seen. Again, it's all in that race to lower the voltage so you reduce the power and the power dissipation for your devices. So that necessitates having a lot of different power on a particular board. And as we talked about that in the PCB talk last week, you want to sort of isolate those. So it's very clear when you go from a 5 volt to a 12 volt or a 3.3 volt to 5 volt, it's really important. It's critical to understand that from the PCB perspective, but also from the layout perspective. But yeah, the voltages have come down. I don't know how much farther they can go. I think they're at crazy levels now, but they will continue if they can. If technology allows it, they will continue to lower. But everything, like I said, was at 5 volts. The first major design I did was an array processor. It ran at 5 volts and consumed on the order average 1,500 amps at 5 volts. So you're talking about 7,500 watts of power. And that was a huge and it had a bunch of switching power supplies and lots of fans to keep it cool. And all of the power in that device, now I have probably 100 times that capability on my phone at this point. So that's why voltages continue to reduce. That's why we continue to put more and more into ICs. And the impact of that is higher frequencies on PC boards, which affects layout. One of the other things that doesn't often get thought of until it's too late is adding test logic and or test points to your design. That same design I was talking about, the array processor, 25% of the parts count for each of the boards in that array processor was test logic. We could look at all the internal registers. We could get access to internal registers. We could read and write the memory in the array processor. And this allowed the software development team to significantly and quickly and easily debug their code and work on solving problems that otherwise would have taken a ton more time. If you can go in and put the right answer into an intermediate register and then continue testing the rest of your code, it means you don't have to spend a lot of time recompiling and reloading. So having test logic and considering it and allowing for it up front can be very critical and can really help you in terms of bringing a board up. If you can't get to a signal, then how can you check to see if it's right? I mean, that it's kind of one of those self-evidence, but I've done things like, and not necessarily in this design, but I've done things like when you go into the PC board, you know, here, all of the signals are being used, right? All the pins are being used, but I've done things like if this pin was not used, but it was a free input or a free output, I might put a trace here and then drop a via in so I connect up to that with wire later on in the lab and allow me to inject signals or to test signals a lot more simply and quickly. With the BGAs packages and a lot of the signals being brought down into the inner layers of the PC board, you need to think about having some test logic, whether in this case it's on the board or you put something in your schematics to give you access. As the designs get more and more complex, testing and integration is increasingly difficult and can actually cause a lot of time and delays. So consider having test logic added into your basic designs. Okay. Go to here. Again, this design, you know, is fairly, it's not too complex, but it was pretty good. Open up, please. And the Xilinx, it's an FPGA based design. This is one of the standard examples that you would get when you load up Altium Designer. It's in your examples folder. So as you can see, you know, a lot of these signals you won't be able to probe. I mean, getting to this finger right here would be very, very difficult. But because it goes through some vias, you might be able to get access to that on the bottom of the board. Again, think about how you're going to get access to some signals that you might want to get to. So let's talk a little bit about part choices. We always make trade-offs during design, and that's both the excitement and the struggle of engineering is you have to make trade-offs. One example is a Bluetooth enabled design. Everything's going Bluetooth, everything's going wireless, everything wants to, the Internet of Things is a big buzzword. And when you have a Bluetooth enabled design, you typically have things like a Bluetooth chip, an RF chip, for example. You also typically would need an antenna, for example. Now, with that comes a trade-off. If you have both a Bluetooth chip and independent antenna, you now have to route between the chip, the Bluetooth chip, and the antenna, an impedance controlled line, and protect it and put guard bands around it. And that takes a lot more work. It also means that you have to be more careful in the PCB fabrication. It requires having a controlled impedance. If you don't have the right impedance, then you're going to get reflections, you're going to get EMI, you're going to get reduced performance, reduced distance, and or maybe it might not work at all, depending on how bad it is. So one of the options, one of the trade-off that you could make in your design is to say, well, let me look at the cost of a Bluetooth device with a built-in antenna. Or let's look at a Bluetooth module that has an SMA connector for an antenna built into it. So I don't have to do any impedance controlled routing on my board. You may find that that A would be faster to implement because it's less constrained, and B, it might not cost as much as a discrete implementation, and you know that it works because it's a module that you've already bought. So while it might be more expensive, it might not be more expensive. It also represents a much lower risk because it's a proven design and it's in production already. So consider all of the factors when you're particularly picking certain parts, like, you know, having Bluetooth enabled. Again, that brings up, as we've said, parts and components are not just, you know, they just don't live in the schematic. They have to live in the PCB realm. So you need to understand how one parts choice affects both the schematics as well as the PCB. And for example, like I said, the RF device, not having to have controlled impedance means the board can be made a lot more cheaply. And again, using a device that's already proven lowers your risk. Now, a lot of the devices I have done have independent antennas, but this is a proven design that we've already worked on for a couple years. So I won't say it's cookie cutter, but I will say it's pretty low risk because, again, of the design reuse. We've used this design before. We understand the trade-offs, and we can just go ahead and drop that in and go. One of the other parts that is somewhat important is when you're considering a design, and I have this issue with a customer. There's a new chip from a company that does basically high-end video processing in their chip. It's a very high-end video processor. It is a very large BGA package, which brings up the last point about parts and component selection for in your schematic. Again, you need to be able to get this onto the board. This particular package, I can easily make the package footprint, but what I couldn't make was the 700 some odd pin schematic part. Nobody had it anywhere. I couldn't get it, so I'd have to create it from hand, by hand. So parts and components need both the schematic symbol and a PCB footprint. And if you can get access to components that have both, lowers your risk, makes it faster and easier to implement. So it might be better to do something with a few more components that you have access to than to use a component that does it all, but you have to create a footprint and you have to create the schematic symbol. If you don't create the footprint properly, or you don't assign the right signal names to the right pin numbers in your schematic symbol, you're going to look at it and say, it's right, why isn't it working? But it's not right because it wasn't created properly. So most people underlook the importance of components. They are critical. So not just parts choice, but what you get with your parts, the components. One of the nice features that Altium has is the manufacturer parts search panel. In this case, let me expand it a little bit more. Come on. I'm thinking I'm blocking some of that, so let me move this down a little bit here. So the manufacturer parts search panel gives you the opportunity to search for parts. So you use a part number in your search, and I've already done this. And I was just looking for a 2N222, just a basic transistor. The nice part about it is for any device that has this little funny bug, this little IC symbol here, that means if I right click on this and do a place, it will pull in the symbol for the schematics as well as a footprint. So that, and I know that this is a verified symbol and footprint, so there's no risk doing this. The other nice feature about this is I see options. If I hit the SPN, it gives me options. It tells me where and how much of this component exists. In this case, there's 7,221 at Newark, and it's 62.5 cents a piece. You buy quantity one. So this gets at, is the part made of unobtainium? Can I buy it? Can I get it? Can I get it delivered? And this tells you not only is it available, and it's, I mean, it's not too bad a price, but it tells you that you can use the part, and now you can actually implement it in your schematic as well as on your PCB. So again, saving a lot of time. Yes, there's a number of times when I've had to create both a symbol and a footprint by hand. I do it. Yeah.
This is a neat feature. So I have how does it pull this information?
It goes through the part suppliers and utilizes the databases that we have access to. So so here's the generic, category of discrete semiconductors. You can look, capacitors. There's a lot of different things that you have here. So I typically do a search for a part number in the part search, but it'll go out with that part search and look online on the available online databases from the various suppliers. That's a whole nother conversation about how you set up your preferred supplier list and what currency you're in, and you can set all that up and you can optimize it. I mean, personally, I like working with DigiKey, but if Newark is the only one that has it, I'll go to Newark. I just have preferences with DigiKey because preferences come as a result of practice, and I've had good experience with them. And I like the fact that I can upload a bill of materials from Altium in spreadsheet format and dump that into their order, and it automatically takes the number of parts that I want per board, and I can do a multiplier for the overall board count. And so it's very simple, very straightforward and easy. They make it easy for you to buy parts from them. Go figure. So that's why I typically use DigiKey, but there are other options, obviously.
Great. So I actually have a couple follow-up questions here.
Sure.
Who typically chooses the parts in the process? I assume they mean between designers and engineers, I assume.
What's that?
Who typically chooses the parts, the components?
Classically, it's been the electrical engineer designing the board. Not the board layout guy, but the electrical engineer. Usually the board layout guy gets stuck with whatever the designer's done. And if you don't want them coming after you, you'll pick parts that have footprints, for example. Otherwise, you're going to have a delay. And the layout engineer said, hey, it's great. Got this part made of unobtainium. Let me go. It's going to take an extra week because I've got to go get and create a footprint for you. So do yourself a favor, only use parts that you have footprints for, unless you really hate your PCB layout guy. Now, there's exceptions, obviously. Some parts are just what you need, and so it's worth it. But again, it takes time, and there's risk, because if you create a footprint that's not right, then you may not be able to fabricate the board. So that's a critical, decision point. Normally what happens, like I said, is the PCB engineer has to deal with whatever they've been given. That doesn't mean they won't come back and say, we can't find this footprint anywhere. You know, are you sure you want us to try to create it? There's risk involved, or it's going to be a delay. Is there another part that we can use? Sometimes there is, not always, but sometimes there is. The typical experience I've had is not so much because I think about the PCB side, which I never did when I was initially designing. So I don't normally have that problem now. The problem I typically still run into is, can I buy the parts? Which is why the manufacturer's part search is so nice, because it says, look, there's 1,000 or 2,000 of those in stock. I need 5 for my prototype run. Woohoo, I'm good. You know, that makes a big difference. Later on, if you're, you know, in a full up company, you'll be doing things like getting a phone call from purchasing saying, we can't find this part. Do you have an equivalent that we could source? So now you've got to stop whatever it was you were doing, go back and figure out what that component was, what the parameters that are important to you. Typically for me in a capacitor, it's the voltage level, it's the package size because we need it to still fit on the board, and it's the capacitance value, right? So voltage, capacitance value, and footprint, or basically the body. And quite often there's a lot of options, but that's one of the things that I've seen quite often too. So it's nice, for example, this particular Infineon part here, it's a power FET. There's a lot of places where we could get this from. So I'd be very comfortable picking this part if it met my needs, because I can get it from a lot of different places. And that's critical. Again, long-term success, it's critical. So
I've got one more question right now.
Yep, hit me.
Let's see. Okay. All right. So, is the recommended design concepts, including dummy components, used for lab reliability tests or more for real applications?
I didn't catch part of that question. Is that on the Q&A?
It is, yeah.
Dummy components that we used. I don't understand the dummy component part.
I might be asking about testing versus production. Maybe.
Yeah, I know. Yeah, dummy components. Yeah, I'm not sure what that reference is. Could we maybe unmute Mohammed and ask him?
Maybe. Mohammed, are you there?
No, I see him.
Yeah, I can see he is unmuted, but he's not speaking.
He may not have a microphone.
Yeah, maybe not. Okay, well, we can come back to it if it comes up.
Sure. Again, Mohammed, I'm not sure what you mean by dummy components. So that I don't understand that. So maybe a little more clarity would be very helpful. But as I said, components need footprints and symbols. Do yourself a favor, make sure you have both. And obviously, secondarily, that you can buy the parts. Again, it's kind of a critical thing. So, as I said, components need to be available. Now we get to the part that nobody likes. At least as a designer, I never liked it. It's incredibly useful, but I never liked it. And that is checking your design. Now, in Altium, there are live electrical rule checks that go on in the background every time you add a component, add a wire, add a net. And basically, it'll yell at you if you assign a reference designator that's the same as another one already in your design. It'll give you little squiggly lines and complain, and that's a quick, easy visual way to understand that, in fact, hey, you screwed up. We'll go back to the PCB view. You know, if I pick this guy here and change capacity designator C5 to C6, you'll see the little squiggly lines on either side. That says, hey, there's a problem. And typically, in this instance, it's because you have the same reference designator between the two of them. I'll undo that, of course. At some point, you may get things like floating inputs, unconnected inputs, multiple drives on the same net, and that would typically show up in your message panel. Certainly any errors like unconnected inputs would show up in your message panel, and you'd want to double check that and fix that. So that's the basic thing that you can do yourself. Much like in the PCB world where you run your design rule checks on the PCB, you would do that yourself. But that's the base level. You'd want to make sure that you've got all of this squared away and clean. And then you'd want to go to the next level of checking your design, and that is the dreaded design review. If you've done a good job with your schematics, and if you have done a good job with your all the notes, all the details, you've created the proper net list formats, you've created all the graphics and organize things properly. That makes a big difference when you go to do a design review, because presumably it's people that don't know your design, and they're going to want to look at this and walk through the design to understand. They'll ask you lots of questions. One of the things I found happens, if it's going to happen, quite often it happens when they're saying, could you explain how this works? Kind of walk us through the process, what's going on in this board. Usually about a third of the way into it, you go, oh, yeah, that's not going to work. And then you make a note because you realize in the process of explaining to somebody else, you realized you overlooked something, or there's something that needs to get changed or fixed. But often, if you make your schematics clear enough and easy enough to follow, you'll get good questions from design review panels. And again, it's a way of reducing risk. And even though it's just at the schematic stage, there's a lot of work that goes into a PCB layout, especially a complex one. So you don't want to go through the process of laying it out and then realizing you need to rip up some logic or reroute some logic or change the device. Things like, I've had things like an engineer said, I know that part's on the approved company list, but we never use it because every now and then you just can't get it. It's just not available. There's a weird supply issue. So it's not written down anywhere. Nobody knows about it, but it's one of those things that everybody avoids that part. And that's really valuable because it means your design can be built when you need it built. And as often as you need it rebuilt, you can do that. So it can be frustrating to have a design review, but at the same time, it saves a lot of aggravation in the long run, and you have a higher chance of success with your design. So one of the things I'll leave is I've been doing design for, it'll be 40 years this spring. I'm still learning. I'm still growing in my understanding of how to do design, how to do the trade-offs in the schematic entry fields. I'm still learning. I've got boatloads to learn still in the PCB world. And it's one of those things that I find really, really fun and challenging, is that I'm still learning. So after 40 years almost, I'm still learning. And that's because the industry is growing and the challenges are changing. Carlos says, how could we improve the testing and find a faster way if we need to change any component to avoid obsolescence? Good practices obviously are not recipes that you suggest. One of the things that I ran into with the design 7 months ago, was I used a very unique part. Like nobody else in the world made it, because it was exactly what I needed. And when you couldn't find it because they decided to stop making it, it's a voltage controlled amplifier, in case anyone was wondering. for my analog synthesizer project, essentially. I have since found another alternate source. The problem is it's a completely different pinout, so I have to redo the board if I want to continue making it. So it's better to try to create your designs based on more traditional standard parts. Like I said, in some cases, you have to use something that's unique. If you have to, you have to. But understand that's a risk and inform purchasing, that you want to make sure that any end of life notifications or obsolescent notifications, you need to consider what you need to purchase to cover your expected lifespan for the board, or conversely, how much you should buy in order to cover the amount of time it's going to take to redesign the board. And that is a guess, but I've seen that in a couple of places. One of the companies I worked at very early on was Gould AMI. They did ASICs, and one of their bread and butter operations was taking existing customer designs and converting them and reproducing them because they had stopped being made by the original manufacturer. And that was a huge business for Gould AMI for a couple of years. It was just planned obsolescence, and they had the right technology that they could mimic a lot of what was done. Obviously, something like an RF chip they couldn't do, but a lot of stuff they could. And it was really quite fascinating that you could actually create a pin-compatible drop-in replacement chip for a lot of stuff. A lot of it was like, glue logic and that sort of thing. And they did a lot of that work because there was a huge demand. I don't know that they're still doing that now. But so the warning is, try to use more standard parts in a more standard way, and you shouldn't trip up. You shouldn't get tripped up on part obsolescence. How early are design reviews typically held, and do I recommend holding several early design reviews at the beginning stages? I do recommend collaborating with others, especially if it's a very complex design. And typically you're going to have to collaborate with others because I should probably just switch to the questions since that's where we are at. Quite often, well, the array processor design, I worked on the sequencer program memory board and the addresser loop counter board, and that interacted with all the other boards in the system. So there was a constant interaction with the other designers for those boards. Now with Altium, it's easier to share and show. And in those days, literally, we were laying lead. I had a D-sized sheet of paper on a draftsman board, and we were capturing schematics the old-fashioned way, which was brutal every time you had to make a change. Just absolutely brutal. But with Altium, there's no reason not to collaborate and share your designs and get feedback from your compatriots. But typically, we would hold a design review minimally, I should say, before we sent it out for layout, because that was a big expense. We didn't do any layout in most of the companies I worked at early on. Everything was done. It was done out of house. So you spent a lot of time verifying and validating that things worked. We did things like timing verification, functional verification. We'd walk through the data flows and the control, and to make sure that everything worked and the timing was right before we would release to a PCB layout. It's more flexible nowadays, again, because things are more fluid. It's easier to update and it's not unusual to have a PC board be updated midstream of layout. That's one of the ugly truths that nobody likes to admit. But designers sometimes, not that any designer would ever do this, but they release a design early to make their boss happy, and then they go on and continue to fix it. Never had that happen before, just saying. But that happens, and so to answer the question, you should have them early, but you should at least have them minimally before you start layout, because the layout is a lot of work and represents a resource that is typically limited in most companies. How do you know what standard parts are? It's a good question, Patrick. There are certain basic building blocks that everyone has, MOSFETs, basic transistors, LEDs, all the bubblegum logic, PIC chips from microchip. I mean, these are all standard parts. When you start talking about non-standard parts, for example, the almost 800 pin ball grid array custom video processing chip, that's the only one of its kind. There are other chips that do video processing, but their internal architecture is different, their pinouts different, their capabilities are different. And so a standard part uses standard voltages, is available in large quantities or lots of variations. I mean, how many different microchip PIC devices are out there? For the 8-bit PICs, there's, I don't know, 50. I don't know, there's huge numbers of them. For 16-bit PICs, there's a whole bunch. 32-bit PICs, I think there's at least 3 or 4 anyways. Maybe 6. And Microchip is a large company that ain't going away. So it may be a PIC, but it really is sort of a standard part. Whereas the voltage controlled amplifier chip that I have currently comes from a company called THAT, T-H-A-T. It's out here in near me. It's in Massachusetts. They're the only company in the world that makes it. Only company in the world that makes the voltage controlled amplifier chip that I use. They go out of business, I got to redesign. So that's a very obvious custom singular component. To replace that component, by the way, would require roughly about 50 parts. And those parts wouldn't perform as well as a single integrated circuit, which is why I went with that particular design. And again, this is a hobby design for me. So I don't need to necessarily have access to 50,000 parts a year for the next 5 years. I'm fine with, a couple of dozen samples and I'm good for, quote, my lifetime for this design. But again, the standard parts are more available and ready. I mean, another good indication is how many places create, for example, or make a 2N2222 transistor. All the major manufacturers make that generic, just like most of the manufacturers make generic FETs. Most of the, LEDs, they're not a dime a dozen. They're actually probably a dozen for a dime, but everybody makes LEDs and leaded, surface mount, those are, so anything that's commonly available and certainly multiple sourced, commonly available, I would consider a standard part.
So, Chris, how are you doing? Hello, Chris.
Okay, I don't see.
I hear somebody trying to speak, but it's really quiet.
The only person that could be is Mohammed.
My sound is still like very low.
It is very, very low, sir. Yes.
We can hear you.
Oh, really? Now it's better or it's still the same?
A little better.
We can hear you.
Okay. So the question is that like about the dummy components. So
Right.
dummy components basically are inactive components, which like they does not have any silicon die in it. So in mechanical testing, we just like have these components without a silicon die because it's costly.
And what do you do them? What do you use them for? Just
Actually, we use this like for vibration testing, thermal cycling,
okay.
mechanical testing.
Yep.
So my question is going to be like these standards is going to be the same, like it's going to be applied for these dummy components, like in terms of copper width, like the thickness of the copper, or like it's going to be, it might be different.
I would, and again, I'm certainly not a reliability engineer. I only pretend, but I would make and use the dummy components exactly the same way that I would use the real components if you want to get valid test results. So if you have heavier copper or different trace widths for your dummy components and the boards and you want to do vibration testing on them, there may be some additional advantage because of the heavier copper or the wider traces that wouldn't show up on your actual real design. So I would make the test board exactly the same as your normal production board, just to avoid any concerns or considerations, if that makes sense.
Yeah, of course, yeah. That really makes sense.
Yeah. I mean, the other thing that occurred to me is I would probably, and maybe it's prohibitive to do, but I would probably want to actually have a real live board for the vibration testing, because I personally would want to check to make sure the thing worked after the vibration testing. And if they're all dummy components, you're not going to know. You're going to know if they fly off the board or if there's damages to the traces and leads, but you're not going to know that the board electrically works if it's all dummy components. So I have not used dummy components ever. I'm not saying they don't get used. I just haven't used them.
Okay. Well, thanks, Mohammed. And I think that's about it.
Yeah.
Any last questions from the crowd?
No.
Okay, we will wrap
Good luck.
up. Chris, thank you for your time. And
Thank you, Aaron. Thank you, everyone. I appreciate it.
And what about follow-up if they have questions from here out?
I think I'd given you my email address already.
I know I have it.
But not in where is the comments? Let me just type the answer here, but put my Jennings. So my Altium email is my name first and last with a dot at altium.com. So chris.jennings@altium.com. I may not be able to answer quickly, but I will try to get back to you if you have questions, further questions. I do believe, Aaron, this was recorded and will be available for the students at some point as well.
Will indeed.
Yep. And for any professors out there, please reach out to me. I'd like to have a conversation with the professors to talk about how to tweak and improve this going forward. My passion is trying to provide some of the insights that I never got in college. There's so many things you learn the hard way once you get out. It's like, if I can give you guys a leg up, do it. Let's do it.
Sounds great. And I've got a few professors that aren't on the call that would be worth speaking to as well.
Yeah, send them my way. We have an outreach with Boulder, University of Colorado in Boulder. There's three professors we deal with there on sort of a regular basis, and they all use Altium, and they use it in a wicked way. And I say that with a smile, but they use it. The students have to use Altium to do their design, to do their PC board layout, and they actually fabricate the boards and have to bring the boards up. So it's like the class I wish I'd had and never could have had when I was in college, because you learn so much by actually taking the board that you've now designed and laid out and then try to get it testing and running. Pretty impressive stuff.
Very cool, yeah.
Pretty impressive. So yeah.
Okay.
Yep. I appreciate it, sir.
Yeah, you too. Thank you for everybody for attending, and thank you, Chris.
Thank you.
We'll end it. Have a good week.
You too. All right. Bye-bye.